In the last two video clips, we've been considering this case of the light clock, and through our analysis of it, we came to this whole concept of time dilation. So what we want to do is pull those pieces together a little bit here and look at where it leads us in terms of a conclusion about time dilation, how we might think about it, and then also consider, is this really real, or is this just some special, almost philosophical case that doesn't apply in the real world? So remember what we were doing here. We had identical clocks, one moving and one at rest. So here's the clock at rest. Perhaps we're Bob, right? So we're Bob sitting here. We've got our clock, our light clock, ticking away with the light beams going up and down. And then we have Alice with an identical clock who is moving with some velocity v with respect to us. Remember, to Alice, she's in her frame of reference, and so as far as she's concerned, her light clock is just bouncing up and down normally. But to Bob, observing her light clock, and by the way, occasionally, I use the term seeing as well. Bob seeing her light clock. Remember, we're using that in a very special sense of technically observing. We're not taking in time delays of light traveling from someplace to your eye and so on and so forth. So if you catch me saying seeing sometimes, just insert observing there, okay, in our precise definition of what it means to observe using a lattice of synchronized clocks and so on and so forth, as we talked about before. So, clock at rest. Bob has his clock at rest. Alice, moving clock. So Bob is observing her moving clock, and our conclusion was that the duration of one clock tick, Bob observing Alice's moving clock, so this is one clock tick, as far as Bob is concerned, observing Alice's clock equals some factor gamma times one clock tick for his clock at rest, which again is identical. So we've got two identical clocks here. And yet by putting one clock into motion, all of a sudden, from Bob's perspective, the clocks are running differently. That the moving clock is running more slowly than his clock at rest, because this gamma factor here, remember, is 1 over the square root of 1 minus v squared over c squared, and that's always greater than or equal to 1. If v is 0, we just get 1 there, but if v is any positive value, any value at all really, because it's v squared, then this number down here will be, the whole thing will be less than 1. I'll have 1 divided by a number less than 1, which will be greater than 1. And in the next video clip, we'll explore some values of gamma a little bit further here to get a feel for what that's like and what values of v give us what values of gamma. But for now, we'll just say that clearly gamma is greater than or equal to 1. So that's where we ended up. Let's draw a little picture here of actually what's going on with this, because really, we're not so interested in clock ticks when we're comparing things. We want to really talk about elapsed time. What's the elapsed time on Bob's clock right here versus the elapsed time as he observes it on Alice's moving clock as it goes by, versus counting clock ticks and things like that. So we need to convert this equation into an elapsed time equation. So let's look at this. We'll just say that gamma equals 3. That's actually a fairly high velocity. But so just to say gamma equals 3, Alice is going by at a fairly high speed. Here, if we're going to sort of create a diagram of the clock ticks, here's what it would look like. So let's look at the rest clock first. The rest clock ticks, okay, so that's Bob here with his clock, just ticking away nicely. So here are the ticks. Each line represents a tick of his clock. And the distance between the two ticks, that's this delta t rest here. That's the elapsed time, the time duration for one tick. The light goes up and comes back down. And then the moving clock ticks, according to our analysis here, with gamma equals 3, we're going to get a tick every third tick for the at-rest clock, right? Because the duration of a tick for the moving clock is 3 times the duration of the tick for the rest clock. Just again assuming gamma equals 3. So we can see we've got 1, 2, 3 rest clock ticks is going to equal 1 moving clock tick. And so again, you get 1 tick of the moving clock every 3 ticks of the rest clock. And all that's saying is sort of in pictorial form what this equation is saying when gamma equals 3. And so clearly we had the moving clock ticking more slowly, from Bob's perspective observing it, ticking more slowly than his rest clock there. Okay? Well, again, we're not so much interested in number of ticks. We want elapsed time. I like to say, okay, Bob measures some elapsed time on his clock. What would be the corresponding elapsed time on Alice's clock as he observes it going by? And we can see this right here is that, the way I've drawn it here, I've got 12 ticks of the rest clock, his rest clock here, is going to equal 4 ticks of the moving clock. Okay? It's a 3-to-1 ratio, again, because we're choosing gamma equals 3 here. So let's just say every tick is 1 second. So on the rest clock, his clock sitting right next to him, he's going to have 12 seconds elapse. The moving clock will only have 4 seconds elapse. Okay? And note that that means it's a slightly different equation than this, and it's really easy to get this switched around. And so that's why we're trying to make a semi-big deal of it here. But let's think about this a minute. We want an equation for elapsed time. Do it right here. So we'll do elapsed time. Elapsed time. Okay. The elapsed time on the moving clock versus the elapsed time on the rest clock. In fact, I'll do it down here. I think it'll be a little easier to write it. So we'll just call it elapsed time moving clock is going to equal something. We're going to leave that blank for him. We're going to fill that in a minute. Times the elapsed time of the rest clock. Okay, so it's the same form as this, except we spelled it out. Elapsed time here equals something times the elapsed time of the rest clock. Here, these were clock ticks, right? The duration of one clock tick versus the clock tick on the other one. We got the gamma factor in there. Okay, clearly it's going to involve gamma, but note what it is here. Just in our example, when gamma equals 3, the elapsed time of the rest clock was 12, right? And so, and then the elapsed time of the moving clock was 4. So we need an equation essentially in that specific example that would say 4 equals something times 12. Well, what is that? It's 1/3, right? 12 times 1/3, 12 divided by 3 is 4. So this number right here is 1/3. In other words, in general, it's 1 over gamma. Okay? You see that again? The duration of each tick for the moving clock, as Bob observes it going by, is longer than 1 tick on the rest clock by a factor of gamma. In this case, gamma equals 3. But that means the elapsed time of the rest clock is greater than the elapsed time on the moving clock. Okay? Moving clock ticks are longer in duration. That means there are fewer of them. Therefore, you flip it around, elapsed time is going to be greater. You're going to get more ticks on the rest clock for the number of ticks on the moving clock. And so this factor right here is 1 over gamma. A very good gamma there. Well, a little bit better. Anyway, 1 over gamma, where gamma is as we've defined it before. Okay? So let's rewrite that so we can see this a little bit better here. And note that this is what we derived using our light clock analysis. This equation here, that's for the ticks. We're going to move away from that now. We said, okay, we derived it. We had this form here. But the new form we're going to write on the board here involving elapsed time, that's the form we want to memorize. And so we can use it in various situations, analyses, and so on and so forth. Okay, so this was our example. Let's erase our example here and say, so we know that the elapsed time on the moving clock equals 1 over gamma elapsed time on the clock at rest. Okay? Again, this is from Bob's perspective. Bob is comparing his clock at rest, his light clock at rest, versus, as the light beam goes up and down, versus the elapsed time on Alice's clock as he sees it go around. Remember, gamma is always greater or equal to 1. So if v is 0, then we just have 1 over 1, and the elapsed time on the two clocks is the same. They're sitting right next to each other. There's no difference in velocity between them, between their frames of reference. But if v is any other value, gamma is greater than 1. So we see the elapsed time on the moving clock is always going to be less than the elapsed time on the clock at rest as Bob is observing it. Here, very important point. It's Bob's observation of the moving clock, or whoever is observing that moving clock, who sees the elapsed time of the moving clock, 1 over gamma elapsed time at their clock, identical clock at rest. So this is where we get time dilation, as we mentioned previously. The moving clock here runs more slowly. Moving clocks run slow, or run slowly, in compared to an identical clock at rest. So sometimes, just to write this in a little better form, we might write it like this. So delta t, well, we use capital T for elapsed time, at least for the moment, because we use lowercase t here. In the future, we may just start using lowercase t's for this equation as well. But for now, we'll say delta t of the moving clock, so an elapsed time on the moving clock, again, equals 1 over gamma times delta t of an identical clock at rest. Right? So that is our time dilation equation. And again, it shows the moving clock runs slow. Now, you have to be precise about this. In fact, a while back, I got an inquiry from a television game show about a question they wanted to ask their contestants, or they were thinking about asking their contestants. And essentially, without going all the details, they wanted a question along the lines of, if you could travel near the speed of light, would time slow down, or time would slow down? So would it slow down, or speed up, or go to infinity, or go to 0? There are a number of different choices. But the answer they thought was correct was time would slow down. Okay? And you can look at our elapsed time equations here. Yeah, well, the moving clock, time slows down. Yeah, that makes sense. Think about it carefully, however, because this is Bob observing the moving clock. Alice, sitting on her spaceship, say, as she's traveling along there at some high velocity v, her clock is just running normally. She does not perceive any difference in time at all. For her, time does not slow down. So that's often when we say things like that, if you could travel near the speed of light, the special theory of relativity says, Einstein says, that time would slow down. Not for the person who's actually traveling at that speed. It's the person outside observing the clock that's moving past that sees time slowing down. And this leads to some things that we'll talk about a little later on in the course, especially the so-called twin paradox of, do people actually age differently, and so on and so forth. But we're not there yet, but that will be coming up in a few weeks here. So, time dilation equation. Delta t, elapsed time on a moving clock, from an observer watching it go by, is 1 over gamma delta t on a clock at rest next to them. Okay? So again, time dilation, we could write it in different form. We could say delta t rest equals gamma delta t moving, but usually it's best to pick one form. This is the form that I think shows a time dilation effect most effectively, because gamma is always greater than or equal to 1. So this will be a fraction like 1/3 if we did gamma equals 3, or 1/2 or something like that. So the moving clock elapsed time less than the elapsed time on the identical rest clock. Okay, so that's time dilation. And again, just to emphasize, this does not mean time slows down for the person on the spaceship, Alice in this case. It means the person observing them sees their clock running more slowly than an identical clock that they have next to them. And of course, you can actually reverse the analysis and have Alice look at Bob, and to Alice, Bob is moving away from her. She will also see her clock running normally and Bob's clock ticking more slowly. And that's where you get into some of these time paradoxes in terms of the twin paradox, which we'll consider later on, figure out how that works. One more thing to do here, though, for time dilation, and that is, you might say, well, this is all very nice, and I sort of see where it comes from, but these light clocks are a little weird. They're strange. How do we know regular clocks work like that? Maybe this is just a special case with these light clocks. And just to also go back to one further point, where this all coming from? Remember, it's because Einstein's two postulates led to the fact that the speed of light is the same for all observers, no matter how you're moving. And therefore, for Bob here, with his clock at rest, he just sees the speed of light going up and down at c. He sees the light on Alice's clock, though taking a diagonal path, also at c. It's clearly a longer path. Therefore, it takes longer to get up and down. In our 3 snapshots here, remember these are the snapshots, 1, 2, and 3, as we watch the light, as Bob watches Alice's light go up and down. Therefore, it ticks more slowly. Okay, but is this just a special case? Well, let's consider that a minute. And early in one of the videos, I promised that we would to make a little argument here to say, no, if a light clock acts like this, all clocks must act like this. If not special theory of relativity, it's true, but if the principle of relativity is true. So let's consider that here. Okay, we're going to go back to our train car. We'll just leave our light clock up there. So here's our train car. And here we are, Alice or somebody is in there. And they have a light clock. Let's get our light clock going in here. So there's our light clock ticking away. And she also has a regular clock in there. So we'll just sort of draw it like that. Okay, so there's a light clock and a regular clock there. And then we have Bob out here, of course, observing. And Alice is moving with some velocity v, some high velocity v. So we'll say this is Alice, Bob observing. Okay. So let's say Bob takes a series of photographs. Again, going back to our photo principle of what's going on. Things in photos have to agree. Both observers, no matter how things are moving, if you take a photograph, they both have to agree that, yes, that is happening at that instant in time and location. So Bob takes a series of photographs here as Alice goes by. Bob is seeing her light clock like this. He's seeing it ticking slowly. Okay? And so you might say, well, again, maybe that's just the light clock. Maybe this regular clock over here, whether it's battery-driven or spring-driven or whatever, maybe it doesn't obey this type of stuff. Maybe it just runs normally. Okay? So what would happen if that's the case? Let's assume that that's true. The light clock is a really special type of thing. This special theory of relativity, all we've been talking about here, really only applies to the light clock. Quote-unquote normal clocks will act differently, will act normally, say. So Bob takes a series of photographs. He sees Alice's clock ticking more slowly, okay, keeping time. Maybe there's a digital readout on that clock, which we compare to this clock, and takes a series of photographs. Therefore, as Alice goes by, Bob will have photographs that show these two clocks are getting out of sync with each other. Because this one is running slow, as the analysis says, but we're assuming this clock runs normally. Okay? So now Bob has a series of photographs that show that as Alice goes by here, this runs slow, therefore they get out of sync. We're assuming they start off in sync with each other. They fly by, and then Bob sees this one, quote-unquote, running normally, running a little faster than this one because of the slowing down effect that we get with our light clock analysis. Okay? So he has those series of photographs. Alice can also take her own photographs at the same time Bob takes his. Okay? Now think about this a minute. Think about the principle of relativity that we emphasized at the beginning. I guess I didn't, well, if we're going to do a train car, I forgot to put the wheels on the train car here, so whatever you want there, or a spaceship or whatever. So whatever it is, going by at velocity v there, think about the principle of relativity and our initial thought experiment we did that we emphasized, saying that for Alice here, inside that train car, assuming she can't look out, there are no reference points which she can tell whether she's moving or not. If she ends up having photographs where these two clocks are running differently, that's evidence that she is moving with some velocity. Because if she's at rest with respect to Bob here, Bob just sees the light clock running normally. That clock's running normally as well, and therefore no difference. But put her in motion, then Bob sees the discrepancy there. If Alice also has photographic evidence of that discrepancy, really just looking at the clocks as she's going along, her photographs would have to agree with Bob's photographs. If every time Bob took a flash photograph as it goes by, Alice also took one at the exact same instant and location and looked at the comparison of her two clocks. If she saw a difference in those two clocks, that'd be clear evidence that she was moving. Because if she wasn't moving, there'd be no difference between the two clocks. They'd both be running normally. Ergo, it would be a violation of the principle of relativity. So you could say, maybe the principle of relativity is violated in a case like that, but Einstein's assertion was, an assumption was that no, it's a universally valid principle. And, of course, based on that and his principle of light constantly, he built the foundations of his special theory of relativity. So in this case, we're going with Einstein. We're saying, yes, the principle of relativity is true. A lot of good evidence that it's true. And therefore, a regular clock, no matter what it's constructed of, has to run the same as a light clock, like we've got here. And therefore, any moving clock runs slowly as Bob observes it. Okay? Not just a special light clock. Now, in principle, you could do a very difficult and complicated analysis of any clock to analyze what's going on, the various motions in the clock, and get the same result. But that's, I suppose in certain cases you might be able to do that, but much easier to just say, hey, if the principle of relativity is true, these two clocks have to run the same in this case, as Bob observes going by. It means they both have to run more slowly than Bob here. He has his, give him his identical light clock here, and give him also a regular clock. Okay? And so his clocks are running normally, perfectly in sync with each other. Alice goes by at some velocity v. Those clocks also have to keep in sync with each other, otherwise a violation of the principle of relativity. Alice could tell whether she's moving or not. And they're going to move more slowly by the gamma factor compared to Bob's two clocks here. So whether we're talking about light clocks or just quote-unquote regular clocks, we get this time dilation effect. And again, remember the basic equation. Delta t, capital T moving, is 1 over gamma delta t at rest. Again, the time dilation effect. And as we move along here in the videos, we'll be exploring more of the consequences of this and also asking some more questions about how some of this actually works.